Hello, I'm Benedict. I'm a co-founder of Foursquare Tutoring, and this is problem 20 from the 2023 AMC 12A. There's this Pascal's triangle looking array that we have to find like the 2023rd row of, and then take the sum of those elements in the 2023rd row, find the units digit. Okay, well, first I'm going to present a solution that I personally did. It's not rigorous at all. It is kind of luck-based. And then I will show you guys how to actually show that solution works. So this first one is sort of just pattern looking, right? Because we have 1 goes to 1. So this is the first row, the sum of the elements in the first row. 2. We have 2 is S2. So right now it looks like powers of 2. 2 to the 0, 2 to the 1. We should expect something with powers of 2 because it looks related to Pascal's triangle. And then if you look at 3, we have 5. So it's not just powers of 2. So 5 is S3. And then here, 12 is S4. And then here is 8 plus 8, 27 is S5. Okay, so how can I relate these to powers of 2? Well, this is 2 to the 5th minus 5. It's also 2 to the 4th plus 11, so this could possibly it. Hopefully it's one of these two. If it's not, then whoops. This is 2 to the 4th minus 4. I'm looking at these two. It's 2 to the n minus n. And it does hold. It's 2 cubed minus 3, 2 squared minus 2, 2 to the 1 minus 1. So from this, if you're doing this and you find a pattern that works for 5 entries, it works. It's the AMC. You're supposed to be able to solve this in like 75 minutes and 25 problems. So let's just say sum of the nth row is 2 to the n minus n. We want to find out what happens when you plug in 2023. S 2023 is 2 to the 2023rd minus 2023. To find the units digit, reduce it modulo 10. The remainder when divided by 10. So this is 2 to the 23rd minus 3 mod 10. 2 to the 2023rd. Powers of 2 cycle modulo 4. So if it's like 0 mod 4, then we're dealing with like a 6 or whatever. But if it's 3 modulo 4, then it's 8 mod 10. The exponent is 3 mod 4. Then 2 to that is 8 mod 10. Minus 3 is 5 mod 10. Hooray! That's it. You could do the more the units digit stuff if you want to just like look at the patterns. But that's the faster solution. Rigorous. So now let's actually try to find a rigorous way to prove why is it 2 to the n minus n each time. Like a pattern is okay on an AMC. That's actually great. They don't have to go through a rigorous explanation on a fast test. But it's now that we're at home, now that we could actually take the time to explain why is everything the way it is, let's just find a way to prove it. So I'm going to start off by listing the elements of the nth row. And those elements are, they're x1, x2, x3, all the way through xn, because we have n elements for the nth row. It's given. So for the elements of the n plus 1th row, we're going to have a 1. Then we're going to start adding here, because we always start with 1. Then we're going to have the 1 plus 3 plus 1, whatever. Then we're going to have x1 plus x2 plus 1, x2 plus x3 plus 1, all the way through xn minus 1 plus xn plus 1, and then 1 at the end. So let's bring out Sn again. So Sn is just x1 plus through xn. Sn plus 1, however, is, let's just add the ones first. We have 2 plus x1 plus x2 plus 1 plus x2 plus x3 plus 1, all the way through xn minus 1 plus xn plus 1. Now everything except for x1 and xn appear twice. So we can bring these over. Remember, x1 and xn are actually the endpoints of the nth row. So they're both equal to 1. So this is equal to 4 plus, and then we can deal with these. We have 2x2s, we have 2x3s, plus 2x2 plus x3, and we also have through xn minus 1 plus xn minus 1. And then now we just have to deal with all of these stray ones that are hanging around at the end. And there are n minus 1 of those, because we have 1 for 1, we have 1 for 2, we're going to have 1 for n minus 1. So this is what Sn is equal to. Wow. I want to get this now into Sn minus 1 because I like recursion. Recursion is nice. Recursion is one step closer to getting to a closed form. So this is equal to 4 plus 2 times. Now to get this to look like another s, we can just add and subtract something. So we can add x1 through xn, but then subtract off x1 plus xn. So this is the same thing. We've just added 0. We've added this, then subtracted them again. And then, of course, plus n minus 1. We can combine these right now. We have 3 plus n plus 2. This is Sn minus, what's this? 2. So this is equal to 3 plus n plus 2, Sn minus 2, or 2Sn plus n minus 1. And that is what Sn plus 1 is equal to. But I don't want it in terms of Sn plus 1. I don't want to have to plug in 2022 and I want to find out what 2023 is. I want to find out what it is in terms of Sn. So to do that, we can just plug in n minus 1. So this gives us Sn is 2Sn minus 1 plus n minus 1 minus 1, or 2Sn minus 1 plus n minus 2. Now, I see these 2's here, and I want to factor them. So we can subtract n from both sides or add n to both sides to factor 2 out of something. Now, it turns out adding n to both sides is the better way to go, but I'm sure you could do something again if you just choose to subtract instead. So adding n, we have Sn plus n is 2 times Sn minus 1 plus n minus 1. So just for now, we're going to call this sequence Sn plus n is Tn, because t comes after s, and I want to keep things a little neater here. So Tn is 2 times, what is this here? I want to get that in terms of t now. Well, Tn minus 1 is Sn minus 1 plus n minus 1. Wow, would you look at that here? Tn is 2 times Tn minus 1. Or we'll write that clearer here, because that is extremely important. Why? Well, now we know that Tn is a geometric sequence. So what's T1? T1 is S1 plus 1, which is just 2. And since the common ratio is 2, we can conclude that Tn is 2 to the n. But Tn is S sub n plus n. So S sub n plus n is 2 to the n, which means that Sn is 2 to the n minus n. Therefore, plugging in 2023, this is equal to 8 minus 3, or 5 mod 10. And finally, we've proven that the answer is choice C.